In this video, we're gonna study about the higher order differential equations and how to solve them in the complementary function and particular integral method. So, the solution to a differential equation will be divided into complementary function and particular integral. So here CF is complementary function and PIH particular integral. So first we will gonna find the complementary function and then we will go to the methods to find particular integrals. So first let's start with complementary function. So we have a table for each of the case and how the case will affect the solution. So let's make the table first. So this is pretty much the table we are gonna follow to get the complementary functions. We have total 1 to 6 cases and there are 6 different type of complementary functions for each different case. So we are gonna study about those in very detailed explanation. So let's go to the first. If the auxiliary equation has the roots, those are real and distinct. Example, say the roots are m1, m2 and m3. So the complementary function will be c1 e to the power m1x, c2 e to the power m2x plus c3 e to the power m3x. Similarly, if the nature of the roots are real but repeated, those are not distinct, like m1 is equal to m2 or m1 is equal to m2 plus equal to m3. So like two or more than two roots are being repeated there. So if two roots are being repeated, then the form will be c1 plus c2x into e to the power m1x. The difference between this thing and this thing is, though there was no x terms in all the constant terms c1, c2 or c3, but if we have anything real and repeated, we have c1, the first term will be out of the power x, but the c2 term will have an x term. Similarly, if we have three roots, those are similar, that becomes c1 plus c2x plus c3x square into e to the power m1x. So similarly, if we have complex roots like m1 is equal to alpha plus I beta, like we have the general form is equal to alpha plus I beta or alpha minus I beta, then the complementary function will be e to the power alpha x into c1 cos beta x plus c2 sin beta x. And again, if we have repeated complex roots like m1 equal to m2 equal to alpha plus I beta or m3 equal to m4 is equal to alpha minus I beta, then e to the power alpha x, that is like, yes, we have the similarity c1 plus c2x, c1 plus c2x into cos beta x. So we have the combination of this thing and this thing that will lead to this thing. So c1 plus c2x from here, that is equal to here, and the cos beta x and sin beta x, those came from this. So this is the combination of the 2 and 3 is the whole 4. Exactly. For the irrational roots, those are not rational, those are not real. So a plus root beta or a minus root beta, that is equal to, we have before cos beta x, we have before the cos x, that was the normal cos function, but in the irrational roots we will use the hyperbolic cos functions, hyperbolic sine functions. And similarly for repeated irrational roots, we will have c1 plus c2x e to the power ax cos h b root bx and c3 plus c4x into sin h root bx. So this whole table is really messy and you are not supposed to understand this in this first half. So we are gonna go detailing one by one from case 1 to case 6 and with real examples, and those examples will make your understanding much better about the complementary function. Alright, so let's begin with the first case, when the roots are real and distinct. So case 1, real and distinct roots. So let's take an example of the case 1, that is let's take the example d square y divided by dx square minus 5 dy by dx plus 6y is equal to 0. Right, so we have an higher order differential equation because this has order 2, so this is an higher order differential equation. So consider d is equal to d by dx and d square is equal to d square by dx square and so on. D to the power n is equal to d to the power n divided by dx to the power n. I want you to please understand these terms, and this understanding will make your solving of higher order differential equation easier and much more simpler. So if we have d square is equal to d square by dx square, so this becomes d square y, right, and this becomes minus 5 dy, right, and this is plus 6y is equal to 0. Okay, so d square minus 5d plus 6 whole into y is equal to 0. That implies d square minus 5d plus 6 is equal to 0. We have our auxiliary equation in the form m square minus 5m plus 6 is equal to 0. This is the general form in which we take d as m to form our auxiliary equation. So m will be minus b plus minus b square minus 4ac, its root over and divided by 2a, right? So this becomes minus of minus 5 plus minus b is minus 5 its square minus 4 into 1 into 6 and its root over divided by 2 into 1. So 5 plus minus 25 minus 24, its root over divided by 2. So 5 plus minus 1 divided by 2. So it becomes 5 plus 1 by 2 and 5 minus 1 by 2. So it is 6 by 2 and 4 by 2, that is 3 and 2. So we have our roots m as 3 and 2. Like I said, 3 and 2 are real and those are distinct. 3 is not equal to 2 and 2 is not equal to 3. So these are real and distinct. So we have to use the first formula, this. The complementary function is equal to c1 e to the power 3x plus c2 e to the power 2x. Y is equal to complementary function plus particular integral. Before I go into the particular integral, I just want you to remember, if there is a 0 in the right side of the equal sign, then the particular integral of the differential equation will be 0. I want to remember this. So y is equal to, the CF is c1 e to the power 3x plus c2 e to the power 2x and the pi is 0. So y is equal to c1 e to the power 3x plus c2 e to the power 2x. So this is our final answer and the final solution to the differential equation we have taken earlier, that is this. Say for example, we had our roots like 1, 2, 3, 4. So our complementary function would have c1 e to the power x plus c2 e to the power 2x plus c3 e to the power 3x plus c4 e to the power 4x. This would have our complementary function. So the first case is now solved. Let's move forward to the second case. Case 2, when the roots are real but repeated or equal. So consider an example. D square y divided by dx square minus 6 dy by dx plus 9y is equal to 0. As I have said before, this will become d square y minus 6 dy plus 9y is equal to 0. That implies d square minus 6d plus 9 into y is equal to 0. That implies d square minus 6d plus 9 is equal to 0. In the auxiliary equation form, it will become m square minus 6m plus 9 is equal to 0. And to solve this, we will go m square minus 3m plus 9 is equal to 0. So m into m minus 3 and minus 3 into m minus 3, that is m minus 3 its square is equal to 0. That implies m equal to 3 and 3. So we have two roots, those are real but repeated. So our complementary function will be c1 e to the power 3x plus c2x e to the power 3x, or c1 plus c2x whole into e to the power 3x, right? Like this. c1 plus c2 e to the power m1x, where m1 is our 3. If there were 1, 1, 2, 3, 4 and 4, our complementary function would have c1 plus c2 x e to the power 1x plus c3 e to the power 2x plus c4 e to the power 3x plus c5 plus c6x into e to the power 4x, like this. This would have our complementary function if our m value was 1, 1, 2, 3 and 4, 4, right? In this way you can solve for the case 2. Let's move forward to the case 3. When two roots are complex. Consider an example, which is d square y by dx square plus 4 dy by dx plus 5y is equal to 0. So d square y plus 4 dy plus 5y is equal to 0. That is d square plus 4d plus 5 is equal to 0. So m square plus 4m plus 5 is equal to 0. Okay, let's use the general formula. Minus b plus minus b square minus 4 into 1 into 5, its root over, divided by 2 into 1. So obviously this will be a complex root, so minus 4 plus minus 16 minus 20, its root over, divided by 2. So m will be minus 4 plus minus, that is 16 minus 20 is minus 4, and minus 4 its root over is 2i, right? 2i divided by 2, that implies m is equal to minus 2 plus minus I. So m is minus 2 plus I and minus 2 minus I. So according to our rule 3, we have alpha plus I beta and alpha minus I beta, where the complementary function is e to the power alpha x into c1 cos beta x plus c2 sin beta x. So here alpha is equal to minus 2 and beta is equal to 1. So our complementary function will be e to the power alpha x, that is minus 2x, into c1 cos beta x, that is cos 1x or cos x, plus c2 sin beta x, that is sin x. So this is our complementary function in the complex roots. Similarly, for case 4, if we have complex roots but equal, consider an equation d square minus 6d plus 25 its square into y is equal to 0. That implies d square minus 6d plus 25 its square is equal to 0. So the auxiliary equation will be m square minus 6m plus 25 its square is equal to 0. So after solving the m, that is m equal to 6 plus minus 36 minus 100, its root over divided by 2, that will be 6 plus minus 8i divided by 2. As we have a square here, so it is written both times, 6 plus minus 8i divided by 2. So we have our roots as 3 plus 4i and 3 plus minus 4i. So we have 3 plus 4i, 3 plus 4i, and 3 minus 4i, 3 minus 4i. As the power of the auxiliary equation is here 4, as the 2 and 2 are multiplied, so we have 4 roots. So we have these two roots as equal and these two roots as equal. So the complementary function will be, so alpha here is 3 and beta here is 4. So e to the power 3x c1 plus c2x into cos 4x plus c3 plus c4x sin 4x. So this is our complementary function. So the case 4 is solved. Now let's move forward to the case 5. In the case 5, we have distinct but irrational roots. Consider the differential equation d cube y divided by dx cube minus 5 d square y by dx square plus 5 dy by dx is equal to 0. That implies d cube y minus 5 d square y plus 5 dy is equal to 0. That is d cube minus 5d square plus 5d is equal to 0. So auxiliary equation becomes m cube minus 5m square plus 5m is equal to 0. That is, after solving m, we have m is equal to 1 and 2 plus or minus root 3. So this is a real root and this is a complex root. So we have to mix our complementary function theory to get the final complementary function. So our final complementary function will be c1 e to the power 1x plus e to the power 2x into c2 cos hyperbolic root 3x plus sine hyperbolic root 3x. So we have used this formula where our a is 2 and b is 3. Now the final repeated irrational roots. So case 6, repeated irrational roots. Consider an example d square minus 4d plus 1 its square into y is equal to 0. That is d square minus 4d plus 1 its whole square equal to 0, and the auxiliary equation will m square minus 4m plus 1 its square is equal to 0. So m will be 4 plus minus 16 minus 4 root over divided by 2. So m will be 4 plus minus 12 root over divided by 2. So m will be 2 plus minus root 3, as there is a square here, so this is taken twice, right? So the complementary function will become y is equal to e to the power 2x c1 plus c2x into cos hyperbolic root 3x plus c3 plus c4x into sine hyperbolic root 3x. Right, here a is our 2 and b is our root 3, so e to the power x, and for repetition we have c2x, c4x, and for our irrational roots we have hyperbolic functions, and this is our root b, right? So all 6 cases are done. We have learned how we can derive the complementary function of any differential equation which has a 0 in the right side of the equal sign. But there is a catch. What about the PI, the particular integral? In this case we have taken all the particular integral as 0. What if the particular integral is non-zero? So let's go to the cases of particular integral one by one. So rules to find the particular integral, right? So we have 5 rules to find the particular integral of the differential equation, and from those 5 rules we have 3 very important rules. Those are asked very repeatedly in the exams, and we have a very unimportant rule, that is number 4 and number 5. We can really skip those, but we're gonna study about the 4, but we are not gonna study about the 5th rule, as this is not included in any types of exams like engineering or BSc. So let's move on to our 4 rules of particular integrals. If the particular integral is in the form of e to the power ax, if in the right side of the equal sign there is no 0, there is something in the form of e to the power ax, then to find the particular integral we have to multiply 1 by f of d into e to the power ax. So remember one thing, that is 1 by d and d. If something is multiplied with d, that is we know d is equal to d by dx, so we will take the derivative of the term. If there is something multiplied with 1 by d, that means it is 1 by d is integration. Okay, so remember this thing. So if there is a term that is in the form of e to the power ax, we will take the a into the place of d and put that in the place of d. So we will see whatever happens. If f of a becomes 0, then we will take the derivative of this term f dash d and put the a in the place of d and multiply with an x. Similarly, if f dash a becomes 0, we will have an x square and we will have a double derivative. So this formula looks a little bit of complex. We can figure this out when we will take an example on this. So why not take an example on this? So example, solve d square y by dx square plus 6 dy by dx plus 9y is equal to 5 e to the power 3x. Okay, so this is d square y plus 6 dy plus 9y is equal to 5 e to the power 3x. That is d square plus 6d plus 9 into y is equal to 5 e to the power 3x. So the auxiliary equation becomes m square plus 6m plus 9 is equal to 0. That is m is equal to minus 3 and minus 3, right? So the complementary function will be c1 plus c2x into e to the power minus 3x. We have the complementary function. Now we will solve for the particular integral. So y will become, this term is divided by this, so 1 by d square plus 6d plus 9 into 5 e to the power 3x, right? Now put this 3 in the place of d, right? So y is equal to 1 by 9 plus 18 plus 9 into 5 e to the power 3x. So y becomes 1 by 36 5 e to the power 3x. So this is our particular integral, that is 1 by 36 into 5 e to the power 3x. We can simply write at 5 by 36 e to the power 3x. So our final answer will be y is equal to complementary function plus particular integral, that is y is equal to, the complementary function is this, and our particular integral this, with a positive sign. So this is how you solve a higher order differential equation, by solving the complementary function and particular integral separately. Let's go to rule number 2, that is 1 by f of d x to the power n is equal to d its power minus 1 into x to the power n. So if there is something x to the power n in the right side of the equal sign, then we have to use this formula. So why not take an example? So example is d square y by dx square plus a square y is equal to a square by p r into L minus x. So this is d square plus a square into y is equal to a square by p r into L minus x. So the auxiliary equation is m square plus a square is equal to 0. That implies m is equal to plus minus ia. So the complementary function is c1 cos ax plus c2 sin ax whole multiplied by e to the power 0x. As we have this as alpha and this as beta, so alpha is 0 and beta is a. So complementary function will be c1 cos ax plus c2 sin ax. Now for our particular integral, we have 1 by f of d. So f of d is here d square plus a square, 1 by d square plus a square into our this a square by pr, a square by pr L minus x. So let's take a square from this term in common, so a square becomes d square by a square plus 1 multiplied by a square by p r into L minus x. So as this whole term is constant, so we can take this into the left of the function of d. So a square by p into r multiplied by 1 by a square 1 plus d square by a square of L minus x. So this a square and a square cancels out, so r by p 1 by 1 plus d square by a square multiplied by L minus x. So r by p, and we have to take this form, the inverse of the function of d. So this goes up of power minus 1, so 1 plus d square by a square of power minus 1 L minus x. As we know from the binomial expansion, so 1 plus d square by a square of power minus 1 is the power minus 1 is multiplied with this, so 1 minus d square by a square multiplied by L minus x. So open this bracket, r by p, so 1 is multiplied by L minus x, so L minus x minus d square by a square of L minus x. So r by p L minus x minus the derivative of L minus x, the double derivative of L minus x. So we know that d is d by dx, so d by dx of L minus x is minus 1 and d square is d square by dx square, so d by dx of d by dx of L minus x. So we have d by dx, and d by dx of L minus x is minus 1, that is d by dx of minus 1 is equal to 0, as minus 1 is a constant. So this whole term becomes 0. So r by p L minus x. So our particular integral is r by p L minus x. and our final answer will be the CF plus PI, that is y is equal to this is the final answer. Now let's move forward to the rule 3. Rule 3 says 1 by f of d square sine ax is equal to sine ax divided by f of minus a square, and 1 by f of d square cos ax is equal to cos ax divided by f of minus a square. So let's take an example, that is d square plus 4 into y is equal to cos 2x. So m square plus 4 is equal to 0. Our auxiliary equation, m is equal to plus minus 2i. So the complementary function will be c1 cos 2x plus c2 sin 2x into e to the power 0x, that is 1. So CF will be this term whole. Okay, now for the particular integral part, we have 1 by d square by 4 d square plus 4 into cos 2x. So that is equal with, we have to put this 2 in the d square term. So 1 by minus a square is minus 2 square, that is minus 4. So this becomes minus 4 plus 4 cos 2x, that is 1 by 0 cos 2x, which is not possible. We cannot solve something like this which deals with infinite. So what can we do? We will do the derivation. Remember, in the rule 1 we have learned that 1 by f of d e to the power ax, if f of a is equal to 0, then take the derivative of the function of d term. So let's take the derivative of d square plus 4, that is 1 by 2d plus 4. The derivative of 4 is 0, and x and cos 2x, right? So we have x 1 by 2d cos 2x, that is x by 2 1 by d cos 2x. What I had told you, the 1 by d represents the integration. So the integration of cos 2x is sin 2x by 2. So x by 2 multiplied by sin 2x by 2. So x sin 2x by 4. So our complete solution is this complementary function plus this particular integral. So this is our final answer by using rule 3. And let's go to the final rule, rule 4. So rule 4 says 1 by f of d e to the power ax phi x is equal to e to the power ax divided by 1 by divided by f of d plus a phi x, where phi x is any arbitrary x function, right? So let's take an example. d square minus 4d plus 4 into y is equal to x cube e to the power 2x. So here phi x is x cube and e to the power ax is e to the power 2x, right? This is the similarity. We can quickly solve for this. M square minus 4m plus 4 equal to 0, so m is equal to 2 and 2. So CF is C1 plus C2x e to the power 2x. Now the particular integral will be 1 by f of d plus a. So here a is 2, so d square, I mean d plus 2 square, minus 4d, I mean 4d plus 2 plus 4 multiplied by x cube, and the e to the power 2x stays in the left. So e to the power 2x 1 by d square plus 4 plus 4d minus 4d minus 8 plus 4 x cube. So e to the power 2x 1 by 4d cancels out, and this cancels out, so this becomes 1 by d square x cube. So this becomes e to the power 2x 1 by d into 1 by d of x cube. So e to the power 2x into 1 by d, and 1 by d is the integration we know, so x to the power 4 by 4, and its integration is e to the power 2x into the integration of x to the power 4 is x to the power 5 divided by 5 into the 4 remaining, that was e to the power 2x into x to the power 5 divided by 20. So e to the power 2x x to the power 5 divided by 20. So our final answer is y is equal to c1 plus c2x e to the power 2x plus e to the power 2x x to the power 5 divided by 20. So this was the whole higher order differential equation, and we learned how to use the complementary function and particular integral to solve the differential equation. Now let's take a final example to just randomize and revise our concepts. So solve d cube y divided by dx cube minus 3 d square y by dx square plus 4 dy by dx minus 2y is equal to e to the power x plus cos x. So it becomes d cube y minus 3 d square y plus 4 dy minus 2y is equal to e to the power x plus cos x. That implies d cube minus 3d square plus 4d minus 2 into y is equal to e to the power x plus cos x. So the auxiliary equation becomes m cube minus 3m square plus 4m minus 2 is equal to 0. So m minus 1 into m square minus 2m plus 2 is equal to 0. So m becomes 1 and 1 plus minus I. So the CF becomes c1 e to the power x plus e to the power x into c2 cos x plus c3 sin x. Then the particular integral is 1 by this term d cube minus 3d square plus 4d minus 2 of e to the power x plus cos x. So let's open this bracket. E to the power x plus again this term and cos x. So this becomes 1 by, here is the e to the power x is e to the power 1x, so here a is 1, so 1 cube minus 3 into 1 square plus 4 into 1 minus 2 into e to the power x. So this becomes 1 by 1 minus 3 plus 4 minus 2, that is 4 minus 2 is 2, 2 minus 3 is minus 1, and minus 1 plus 1 is 0. So this cannot be applied, we have to take the derivative first. So this becomes x into 1 by derivative of this 3d square minus 6d plus 4 and e to the power x, right? X into 1 by 3 into 1 square minus 6 into 1 plus 4 e to the power x, that is x into 1 by 3 minus 6 plus 4 e to the power x, that is x e to the power x divided by 1, so x e to the power x. Again for this term we have 1 by d into d square minus 3d square plus 4d minus 2 cos x. Let's put d square as minus a square, where a is 1, so cos 1x, so a is 1, so 1 by d into minus 1 minus 3 into minus 1 plus 4d minus 2 cos x plus minus d plus 3 plus 4d minus 2 cos x plus 1 by 3d plus 1 cos x. So multiply 3d minus 1 on numerator and denominator, right? Then it becomes 3d into cos x minus 1 into cos x divided by 9d square minus 1, right? And also the minus 1 term now goes to the d square, so 3d cos x minus cos x divided by 9 into minus 1 minus 1. So we know that d is derivative, d by dx, so derivative of cos x is minus sin x, so minus 3 sin x minus cos x divided by minus 9 minus 1, so minus 3 sin x minus cos x divided by minus 10, which is 3 sin x plus cos x divided by 10. So the particular integral is finally e to the power x into x plus 3 sin x plus cos x divided by 10. So the final answer y will be c1 e to the power x plus e to the power x, c2 cos x plus c3 sin x plus x e to the power x plus 3 sin x plus cos x divided by 10. So this is our final solution. Now we have mastered the higher order differential equation Now you can solve any type of differential equation that is thrown on us, and we are now prepared for any type of differential equation. Thank you and best of luck.